Welcome. Today, we are taking a fascinating and I think often overlooked detour deep beneath the surface. We're exploring the huge geological forces and, frankly, the intense engineering needed to harness geothermal power.
That's right. And for this, we're really digging into the kind of authoritative insights you find in works like Ronald DiPippo's on geothermal power plants. He maps out the principles, the applications.
And right away, you hit this central paradox, don't you?
You do. The heat, the Earth's heat, it's everywhere under our feet. But the high temperature resources, the specific kind you need for viable commercial electricity generation, those are actually pretty rare, few and far between.
Okay, let's put some numbers on that. If you're just drilling, say, a regular well in a geologically quiet spot, you'd expect the temperature to go up maybe, 3 degrees Celsius for every 100 meters down.
Yeah, that's the normal geothermal gradient. And look, it's useful for some things, low-grade heat, heating buildings perhaps. But thermodynamically, it's just not enough for efficient steam-driven electricity.
Not hot enough to make power economically.
Precisely. So the resources we're really interested in, the ones DiPippo focuses on, they're found in what he calls these anomalous regions, places with recent volcanic activity or really intense tectonic movement. That's where you find these massive thermal spikes.
Like Larderello in Italy, site of the very first geothermal engine.
Exactly like Larderello. In places like that, the temperature gradient is just astonishing. It can be 10, even 30 times higher than normal.
30 times, which means...
It means you can hit temperatures needed for high-pressure steam, over 300 degrees Celsius at depths of maybe just 1 kilometer.
Wow, that's shallow.
That concentrated, accessible heat, that's the geological lottery win. So understanding the forces that actually create these hotspots, that's really the first critical step.
Okay, let's unpack that framework then. How do we get from a standard 3 degrees per 100 meters up to potentially 30 degrees per 100 meters? Or to start with the big planetary engine, right? The theory of plate tectonics.
Absolutely. Plate tectonics gives us the fundamental blueprint for geothermal exploration. It's kind of amazing to remember that this now universally accepted theory started as a really radical, pretty controversial idea, continental drift. Alfred Wegener back in 1915.
Yeah, he saw how the continents like South America and Africa looked like they just fit together, didn't he? Like puzzle pieces from some ancient supercontinent.
He did. And the resistance he faced was huge, mainly because he couldn't really explain how the continents moved. His idea was they were somehow plowing through the solid seafloor, which didn't make sense mechanically.
So how did the scientific world finally get on board, move from, controversy to certainty?
Well, it took decades. Really, the confirmation came in the 1950s and 60s, mostly from detailed oceanic surveys and geological mapping. One key piece of evidence was matching rock ages and structures across oceans, like the rocks near Recife in Trinidad lining up perfectly with those near Luanda and Sierra Leone.
A physical match across the Atlantic.
A physical match. And then ocean research uncovered this phenomenon of seafloor spreading along the mid-ocean ridges. They found new crust constantly being generated from the mantle below.
Like a giant conveyor belt.
Pushing the older crust and the continents sitting on top of it apart. It proved the continents weren't floating through the ocean floor. They were the plates, part of the plates, constantly moving on this underlying, partially molten mantle layer.
Okay, so the plates are moving. But even with this modern theory, our sources, like DiPippo's work, point out there's still a lot we don't know about the detailed structure deep inside the Earth below the crust.
Oh, absolutely. The inner Earth is still profoundly mysterious, mostly because we just haven't been able to penetrate the crust deep enough directly. Think about Project Moho back in 1966. Hugely ambitious.
That was the one trying to drill through the ocean crust to reach the mantle, right? Crossing the Mohorovicich's continuity. The Moho.
That's the one. The Moho is that boundary layer, separating the solid crust from the much denser, generally molten upper mantle. A Croatian seismologist, Mohorovicic, figured it out in 1909 from how seismic waves change speed.
So it marks a fundamental change in what the Earth is made of down there.
A fundamental change, yeah. And Project Moho aimed to punch right through the thinnest part of the oceanic crust, maybe 5 kilometers thick, and sample the mantle directly.
It failed.
It failed, mostly due to logistics and funding issues, not necessarily because it was technically impossible, but its termination left this huge gap. We still rely mostly on complex seismic analysis, interpreting waves bouncing around down there, to model that inner structure, the exact thermal dynamics deep down. Still models, not direct observation.
Okay, but this plate motion, whether we know every detail or not, That's the source of the concentrated heat we need for geothermal. How does that constant shuffling actually create the right conditions?
Well, probably the single most important mechanism for creating these high temperature geothermal regions, the commercially viable ones, is something called trenching, or more commonly, subduction.
That's when one plate dives underneath another one.
Exactly. Typically, a dense oceanic plate diving beneath a lighter continental plate. And as that oceanic crust sinks, it carries enormous amounts of seawater and water soaked sediments down with it, deep into the hotter parts of the Earth.
Now, a lot of people might think the heat just comes from the friction, the grinding between the plates. Is that right?
That's part of it, sure. There's frictional heating. But the key driver for creating the magma, the molten rock, is actually the water. When that water saturated crust gets deep enough, the intense heat and pressure squeeze the water out.
Squeezed out of the sinking plate.
Right. And it migrates upward into the mantle rock above the sinking plate, what we call the mantle wedge. Now, water acts as a flux. Think of it like adding salt to ice, it lowers the melting point.
Ah, okay. So the mantle rock there, which would normally stay solid even at those temperatures and pressures.
It starts to partially melt precisely because that water is introduced. This partial melting creates these large bodies, these plutons, of lower density, higher temperature molten rock, magma.
And because it's less dense, it wants to rise.
It's buoyant, exactly. So it moves upward into the overlying crust, often stalling out several kilometers below the surface. This rising magma is the direct concentrated heat source we need for high-grade geothermal.
And you can literally see the evidence on the surface, right? That line of rising heat creates chains of volcanoes.
Absolutely. Think about the Pacific Ring of Fire, that nearly unbroken string of active volcanoes running from, say, Guatemala all the way down the Andes to southern Chile. That's the surface expression of these subduction zones and the rising magma they generate.
So those active margins where the heat meets water?
That's where you get the perfect conditions for the most common type of geothermal power. Hydrothermal systems, hot water systems. And it's the continuous movement of those plates that keeps feeding the heat engine, sometimes for millions of years.
Okay, so identifying a tectonically active region like one of these subduction zones, that's just step one. As the sources like DiPippo really emphasize, you need more than just heat down there. You need what they call a commercially viable reservoir.
Right, a specific geological structure that can actually trap and hold that heat and water in a way we can access and use it. DiPippo lays out 5 absolutely crucial features you need for a successful hydrothermal resource that's a hot water or steam resource. Okay, first, obviously you need that large heat source, the magma body we just talked about. Second, you need a permeable reservoir rock. That means rock with enough natural cracks, fractures, or pores to let fluid actually move through it.
Okay, heat source, permeable rock.
Third, you need a supply of water within that rock to actually get heated up. Fourth, you need an overlying layer of impervious rock. We call that the cap rock. It has to be strong enough and tight enough to keep the hot water, the steam, and the pressure from just leaking away to the surface.
Makes sense, like a lid on the pressure cooker. What's number 5?
Number 5 is a reliable recharge mechanism. You need some way for the reservoir to be replenished as you extract the hot fluid. Otherwise, you just deplete it. This could be natural groundwater inflow, or, as we'll see, sometimes it has to be engineered.
So heat, permeability, water, a cap, and recharge, if you're missing any one of those.
You've got a geological failure, basically, or, at the very least, a major engineering headache. Finding all 5 of those features working together perfectly, that's incredibly rare. It's the geological perfect storm.
Right. So what happens when a resource is maybe missing or deficient in, say, permeability or the water supply or the recharge? That sounds like where the engineers really have to step in.
That's exactly it. Engineers essentially have to, well, take over the geological plumbing sometimes. If the reservoir rock is hot, but it's too tight, not naturally permeable enough, they might use hydraulic fracturing.
We hear that term a lot in oil and gas. Is it the same idea here?
The basic idea is similar, yes. Creating flow paths by cracking the rock. But the environment in geothermal is often much tougher. You're trying to fracture superheated rock, often deeper down under immense stress. The goal is to create a network of cracks that lets injected colder water circulate and pick up heat efficiently.
So creating permeability where nature didn't provide enough. And what about if the issue is not enough water or weak natural recharge?
That's absolutely critical to address. Engineers tackle this by re-injecting all the used geothermal fluid, the brine, back down into the reservoir after it's gone through the power plant. But sometimes, even that's not enough to keep the pressure up and replace the mass you're taking out. The most famous example of needing more water is the Geysers field in California. They had to build massive pipelines to bring in treated municipal wastewater from communities like Santa Rosa, miles away.
Wow, piping in sewage water is
Yes. This external fluid source, this augmented recharge, is absolutely critical now to maintain the fluid levels in that huge, partly depleted steam reservoir.
Okay, so once the geology looks promising, maybe with some engineering help, the next step is this sophisticated geochemical survey, reading the fluids basically before you commit to expensive drilling.
Geochemistry is absolutely key in the exploration phase. It works because hot water moving through rock dissolves minerals, and it reaches a chemical equilibrium with those minerals fairly quickly at high temperatures. We can exploit that using what we call geothermometers.
Geothermometers, like a thermometer for the Earth.
Sort of, yeah. They let us estimate the temperature deep down in the reservoir just by analyzing fluid samples taken at the surface, maybe from hot springs or shallow wells. The most common and reliable one is the silica geothermometer.
Silica, like sand. How does measuring silica tell you the temperature miles underground?
Well, it's dissolved silica, silicon dioxide, SiO2. Specifically, it relies on the known solubility of quartz, which is a common crystalline form of silica found in many rocks. How much quartz dissolves in water is very predictably dependent on the water's temperature.
Ah, hotter water dissolves more silica.
Exactly. So you carefully collect a fluid sample at the surface, you precisely measure the concentration of dissolved SiO2 in it, and then you use established solubility curves to work backwards and estimate the temperature where that water was last in equilibrium with quartz rock, presumably, deep in the reservoir.
Okay, that sounds clever. But the sources, DiPippo included, highlight a really big practical challenge with that surface sample. They call it the steam loss dilemma.
Oh, yes. This is a major headache for geochemists. As that hot fluid travels up the well from the deep reservoir to the surface, the pressure drops dramatically. This often causes some of the water to flash into steam before it reaches the surface where you take the sample. The dilemma is, how much steam boiled off, if any? Did the sample you collected remain fully liquid all the way up? That's the no steam loss or NSL assumption. Or did the maximum possible amount of steam flash off along the way? That's the maximum steam loss or MSL assumption.
Why does that distinction matter so much for the temperature estimate?
Because steam carries away virtually no dissolved silica. It leaves the silica behind in the remaining liquid water. So if steam loss did occur, the silica concentration in the water sample you collect at the surface will be artificially higher than it was in the deep reservoir.
Ah, I see. So that higher concentration would make you think the reservoir was hotter than it really is.
Potentially, yes, if you used the wrong assumption. It radically affects the temperature calculation. DiPippo gives a great example. Say you measure 500 parts per million of silica in your sample. If you assume no steam loss, NSL, the calculation might point to a reservoir temperature of 260 degrees Celsius.
Pretty hot.
Very hot. But if you assume maximum steam loss, MSL, occurred, that same 500 ppm measurement might only indicate a reservoir temperature of 230 degrees Celsius.
Wow, a 30-degree difference just based on an assumption about steam. That's huge.
Yeah.
What are the practical consequences of getting that wrong?
Massive consequences. It could be the difference between a project being economically viable or not. Or it could mean you design, say, a high-pressure flash power plant expecting 260-degree fluid, but you actually only get 230-degree fluid. Your expensive plant will dramatically underperform. The power output will be way lower than projected. It's an unavoidable risk assessment based purely on how you think that fluid got to the surface.
Are there ways to double-check or narrow down that uncertainty?
Yes, thankfully. Geochemists use other geothermometers as cross-checks. Ratios of dissolved minerals, like the sodium to potassium ratio, the NOC geothermometer that's particularly reliable in the 180 to 200 degrees Celsius range. There's also a NOC ratio used for fluids rich in calcium.
So different chemical indicators.
Different indicators, exactly. And then there's a whole separate set of tools using gas geochemistry, analyzing the gases dissolved in the steam or fluid, like carbon dioxide, hydrogen sulfide, methane. The equilibrium reactions between these gases are also temperature dependent. By combining all these different chemical clues, the geochemist can triangulate a much more confident estimate of the true reservoir temperature before anyone drills a deep, expensive well.
Okay. Now let's touch on those edge cases you mentioned, the resources that have heat, but maybe lack those other essential ingredients, yet still hold immense potential. Things like hot dry rock or HDR, now often called enhanced geothermal systems, EGS.
EGS is really seen as the next frontier, and it's fundamentally an engineering challenge. It targets rock formations that are definitely hot, often 200 degrees C or more, but they're dry or tight. They lack the natural water or the permeability needed for a conventional hydrothermal system.
So you can't just drill and produce steam or hot water.
Exactly. The concept behind EGS is to basically create the reservoir. You drill an injection well deep into the hot, tight rock, then you pump cold water down at extremely high pressures, high enough to actually fracture the rock, creating an artificial network of cracks.
So fracking again, but maybe on a larger scale.
Yes, creating an artificial fracture zone. And then comes the really tricky part. You have to drill a second well, a production well, hopefully positioned to perfectly intersect that engineered fracture zone you just created miles underground.
Wow. So you're not just finding a reservoir, you're literally building one deep in the earth.
That's the goal, turning a hot, solid, non-productive rock mass into a functional heat exchanger. Our sources mention ongoing research projects, for example, in Japan and elsewhere, but the challenges are immense, trying to steer deep wells to hit a fracture plane that might only be tens of meters wide.
Sounds incredibly difficult.
It is. And then you have problems like fluid loss, where the water you inject just disappears into other uncontrolled natural fractures instead of flowing neatly to your production well, making the whole system inefficient. Lots of work still needed to make EGS truly commercial on a wide scale.
And even beyond EGS, there's this ultimate, almost sci-fi concept, magma energy.
Right. Drilling directly into molten rock. It sounds wild, but it was actually the subject of serious research by the U.S. Department of Energy back in the 70s and 80s. The idea was to tap directly into a magma body, where temperatures could be well over 1,000 degrees Celsius.
Okay, but how on earth do you drill into molten rock without your drill bit just melting instantly?
Well, the proposed concept is pretty ingenious. You wouldn't try to keep the hole open in molten magma. Instead, you'd inject cold water directly into the magma chamber through the drill hole.
Inject water into magma, what would happen?
The idea was the cold water would rapidly quench and solidify the molten rock immediately around the wellbore. It would form this glassy, heavily cracked, solidified zone. Then you'd circulate more water through this extremely hot, artificially fractured glassy material. It acts like a downhole heat exchanger.
So you create your own heat exchanger right inside the edge of the magma chamber.
That was the concept. This system would return superheated fluid, maybe steam, to the surface where you could run a conventional power plant, likely a Rankine cycle binary plant because of the potentially very high temperatures.
Did they ever actually try it?
They did conduct research projects, notably at Kilauea Iki volcano in Hawaii, and also in the Long Valley caldera in California. The Long Valley program was particularly ambitious. It aimed to prove accessible magma bodies existed and develop the specialized drilling tech needed for those extreme environments. The deep drilling effort at Long Valley was eventually halted in 1991. Not because they hit insurmountable technical problems, apparently, but mostly due to a shift in DOE policy, moving away from that kind of fundamental high-risk research. The last well reached over 7,500 feet, but didn't quite hit its target temperature of 500 C. Still, that research provided a lot of foundational knowledge for any future attempts at ultra-deep, ultra-hot drilling.
All right, so we've used the science, the geology, the geochemistry to hopefully identify a viable target. Now comes the really dramatic part, actually drilling down to access that heat. And let's set the scene with that incredible anecdote from Glenn Truitt back in 1922 describing the very first well at the Geysers. He said, the well blew up like a volcano, everything came flying up, mud, tools, rocks, and clean steam.
Yeah, that image really captures the immense raw power that drilling engineers have to control and tame. The standard way it's done in the industry is rotary drilling. You have this huge engine on the surface rotating a long string of drill pipe.
And at the bottom of that pipe string is the drill bit doing the work.
Exactly. And the workhorse bit, especially for harder rock, is the tri-cone roller bit. That was invented by Howard Hughes Sr. back in 1909. It's got 3 rotating cones covered in hard teeth. Instead of just scraping the rock, it focuses immense force onto those small points, effectively cracking and spalling the rock face. Much more efficient.
Okay, the bit does the cutting. But central to the whole operation, as our sources describe it, is this engineered fluid they call drilling mud. And it sounds like it's much, much more than just a simple lubricant.
Oh, it's incredibly important. It's actually a highly complex chemical mixture, carefully engineered, and it performs 4 absolutely vital functions all at the same time.
4 functions. Okay, what are they?
First, it has to lift all the rock chips, the cuttings that the bit creates, carry them all the way from the bottom of the hole back up to the surface, get them out of the way. Second, it cools and lubricates the drill bit itself, which gets incredibly hot. and the whole drill string rotating in the hole.
Okay, chip removal and cooling lubrication. What else?
Third, and this is critically important for safety and well control, the sheer weight, the hydrostatic pressure of the column of dense mud in the well bore physically prevents the well walls from collapsing inward. And even more crucially, it prevents the high-pressure fluids down in the reservoir, the steam or hot water, from flowing uncontrollably up into the well. It holds the pressure back.
It's the main safety barrier against blowouts during drilling.
It is. And the fourth function is that the mud helps form a thin, impermeable layer called a filter cake on the walls of the well where it passes through permeable rock zones. This stops the well walls from eroding and also minimizes how much of the drilling fluid itself leaks away into the surrounding rock. It's like sealing the edges.
But this drilling mud, essential as it is also the source of a major headache for drillers, something called lost circulation, or LOC.
Yes, lost circulation. That happens when the drilling mud encounters a very permeable zone underground, maybe a large natural fracture or a zone of porous rock, and instead of circulating back up to the surface, it just flows out into the formation. It gets lost.
And if you lose all the mud returning to the surface?
If you have total lost circulation, the driller instantly loses 3 of those 4 vital functions. You lose chip removal, the cuttings just build up around the bit, you lose the primary cooling for the bit, and most dangerously, you lose that hydrostatic pressure holding back the formation fluids. So in shallow, cooler parts of the hole, LOC is a huge problem. You basically can't continue drilling safely without getting mud returns back.
Okay, so LOC is bad. But the sources say that once the drill bit actually reaches the target production zone deep down, hitting total LOC can actually be a cause for celebration. How does that work?
Yeah, it's the driller's constant paradox. Hitting LOC in the production zone is usually a great sign. It indicates excellent permeability, exactly what you want for a productive well that can flow lots of steam or hot water.
So it signals you've hit the jackpot, geologically speaking.
Exactly. But imagine the tricky decisions if the driller encounters, say, partial lost circulation in the upper part of the hot reservoir zone. Do they stop drilling and try to cement off that lost zone so they can continue deeper safely? But maybe cementing it seals off a potentially valuable connection to the main reservoir. Or do they risk drilling ahead with poor fluid control? These kinds of judgment calls, especially when exploring a new field, can really impact the field's overall efficiency later on.
Okay, so assuming they successfully drill the well, the next critical phase is running and cementing the casing. That's the steel pipe that lines the wellbore. And this is described as being fraught with potential disaster, this casing crisis.
It's a very high-stakes operation, yes. The goal is simple. You lower the heavy steel casing pipe into the hole, and then you pump specialized cement down the inside of the casing. The cement flows out the bottom and back up the outside, filling the gap, the annulus between the casing and the rock wall. When it sets, it should bond the pipe securely to the formation along its entire length.
Should being the operative word. What happens if it doesn't work perfectly?
The big danger is if the cement encounters one of those permeable zones, maybe a lost circulation zone, on its way back up the annulus. If a significant amount of cement flows out into that zone instead of filling the annulus space above it, you can end up with a section of casing that's not properly cemented. It's just held in place by maybe some leftover drilling mud residue.
And why is that uncemented section so incredibly dangerous once the well starts producing hot geothermal fluids?
Because that annulus space, that gap behind the uncemented casing, is now trapped, and it's typically filled with leftover liquid drilling mud, maybe some water. Now, when the extremely hot geothermal fluids start flowing up inside the casing during production, that heat conducts through the steel casing wall and starts dramatically heating up the trapped liquid in the annulus behind it.
And liquids expand when heated.
Exactly. And because that liquid is trapped in a confined space, it can't expand freely. The pressure builds up incredibly rapidly, massively. Enough pressure can build up to actually collapse the steel casing inward, crushing it like a tin can. Or, potentially even worse, it could cause a catastrophic failure where the pressure blows out through a weak point at the surface connection. A major blowout.
That sounds terrifying. And the repair, this squeeze job, sounds just as risky.
It is intensely risky and difficult. It involves trying to force more cement down from the surface under extremely high pressure into that problematic uncemented annulus. You're trying to displace the trapped fluids and mud residue and get a proper cement bond, often years after the initial cementing job. It's tricky. One technique that was pioneered in geothermal to mitigate this risk before production starts is to deliberately heat the casing first, maybe by circulating steam or hot water through it. The goal is to boil off any trapped liquid in the annulus, replacing the incompressible water with compressible steam or air. That significantly reduces the pressure buildup risk if that section gets reheated later.
Smart. Finally, on drilling in wells, safety protocols have to account not just for pressure, but also for the specific chemical hazards in geothermal fluids. Standard oil field tech like blowout preventers, BOPs, are used, but the gas risk is different.
Yes, that's a key difference. Geothermal fields often produce significant amounts of non-condensable gases mixed in with the steam or hot water. The main culprits are usually hydrogen sulfide, H2S, smells like rotten eggs, very toxic, and carbon dioxide, CO2. Now, the crucial thing is both H2S and CO2 are heavier than air.
Heavier than air, so they don't just float away if there's a leak.
Exactly. They tend to sink and accumulate in low-lying, confined spaces. The well cellar, the excavation around the wellhead at the surface, is a classic danger zone. If there's even a small leak, these invisible, toxic gases can build up to lethal concentrations very quickly down there. Constant gas monitoring, alarms, and robust forced ventilation systems are absolutely non-negotiable safety requirements around geothermal wellheads.
Okay, we've successfully navigated the geology, the geochemistry, the drilling hazards. We've found the heat, tapped into it, controlled the pressure. Now we get to the surface equipment, the power plant itself, the systems that actually convert that heat into electricity. These seem to fall into several distinct types, starting with the simplest, but using the rarest resource, the dry steam plants.
Dry steam plants are the simplest, yes, because they use the absolute best-case geothermal resource. Pure, dry, or maybe even slightly superheated steam coming right out of the well. But as you say, it's a geological unicorn. Only a tiny fraction, maybe 5% or so, of the world's high-temperature geothermal systems naturally produce dry steam instead of hot liquid water.
And the big examples are still Larderello in Italy and the Geysers in California.
Those are really the only two very large, commercially exploited dry steam fields globally. It takes a very specific, almost fortuitous set of geological circumstances to create one.
What are those circumstances? What makes a dry steam field so rare?
Well, you need the hot magma source close to the surface, obviously. But the critical factor seems to be the hydrogeology above the main heat source. You need highly permeable rock pathways that have allowed steam to escape naturally over very long geological timescales. This sustained steam loss effectively boils off the water table, lowering it dramatically, creating a large underground zone that's dominated by vapor, by steam, instead of liquid water.
So the water level drops way down.
Way down. But crucially, you also need very effective lateral sealing. Impermeable rocks surrounding the steam zone, preventing cooler groundwater from the sides from flooding in and quenching the system. If the natural steam escape rate is higher than the rate of water intrusion from the sides, you can maintain a stable, large, vapor-dominated reservoir, a dry steam field.
And because the fuel is just pure steam, the power plant design is straightforward.
Relatively straightforward, yes. The steam from the wells is piped directly into a turbine, which spins a generator. Pretty simple. The main operational complexity often lies in dealing with the non-condensable gases mixed with the steam and the sheer size of the condensers needed. Geothermal steam is usually at lower pressure than in conventional power plants, meaning it has a very high heat of condensation that needs to be removed. So the cooling towers in condenser systems are often huge.
Okay, but since dry steam is so rare, let's move to the real workhorses of the industry, the flash steam power plants. These use the much more common liquid-dominated geothermal resources, starting with the basic single flash design.
Right. The single flash plant is kind of the standard configuration when your wells produce very hot pressurized liquid water, often called brine. It works by drastically reducing the pressure of that incoming geofluid as it enters a large vessel on the surface.
And reducing the pressure makes the hot water boil.
Instantly. A portion of that superheated liquid flashes into steam. This usually happens inside a big cyclone separator. The centrifugal force spins the heavier liquid brine phase outward and downward, while the lighter steam phase gathers in the center and goes upward off to the turbine.
Simple separation. Now, the sources, like DiPippo, talk about a really important engineering rule of thumb for optimizing how much steam you get out of this flashing process.
Yeah, it's all about maximizing the useful work you can extract. The rule of thumb states that the best temperature to flash the liquid at, which corresponds to the pressure inside that separator vessel, is usually close to the average temperature between the original deep reservoir temperature and the final temperature in the power plant's condenser, where the steam turns back into water.
The average between the start and end temperatures. Why is that the sweet spot?
It's a thermodynamic balancing act. If you flash at a very low pressure, meaning a low temperature, you'll boil off a larger mass of steam. But that steam will be at low pressure and contain less energy per pound. If you flash at a very high pressure, closer to the reservoir pressure, you'll get less steam mass, but it will be higher quality, higher energy steam. The optimal average temperature typically maximizes the total power output, balancing the mass flow and the energy content of the steam going to the turbine.
Okay, that makes sense. Now, to try and wring every last bit of useful energy out of that hot brine, engineers often go a step further to a double flash system. How much more efficient is that?
Significantly more efficient. The big advantage of double flash is that it utilizes the heat still remaining in that hot liquid brine after the first flash stage. In a single flash plant, that hot brine, often still well above boiling point at atmospheric pressure, is usually just re-injected back underground straight away.
So you're throwing away potential energy.
You are. In a double flash plant, that hot brine leaving the first high-pressure separator is instead sent to a second flash vessel, operating at an even lower pressure. This causes more of the remaining liquid to flash into steam, although the secondary steam will be at a lower pressure and temperature than the primary steam.
So you get two streams of steam, one high pressure, one low pressure, going to the turbine, or maybe different stages of the turbine.
Exactly. It's definitely more complex, requires more equipment, two separators, maybe a more complex turbine. But under the same reservoir conditions, DiPippo notes that a well-optimized double flash plant can generate roughly 31% more gross power than an optimized single flash plant. That's a huge improvement, often well worth the extra capital cost.
31% more power from the same wells. That's significant. Okay, finally we get to the third main type, binary cycle power plants. These seem to be used for resources that aren't quite hot enough for efficient flashing.
That's right. Binary plants are the solution for lower to moderate temperature geothermal resources, maybe down to around 100 degrees Celsius, sometimes even a bit lower, where flashing to steam just wouldn't produce enough usable pressure. They work based on the Rankine cycle like many power plants, but they use a crucial intermediary step.
They don't use the geothermal fluid directly in the turbine.
No, they don't. Instead, the hot geothermal brine from the wells flows through a closed-loop heat exchanger on the surface. Inside that heat exchanger, the brine transfers its heat to a secondary fluid called a working fluid. This working fluid is typically an organic compound, often a hydrocarbon like isopentane or isobutane, which has a much lower boiling point than water.
So the geothermal brine boils this other fluid.
Precisely. The heat from the brine boils the organic working fluid into a high-pressure vapor. That vapor then expands through the turbine, driving the generator. Meanwhile, the geothermal brine, having given up some of its heat, never actually flashes or boils itself. It remains a pressurized liquid throughout the process and is usually re-injected directly back into the reservoir.
That sounds cleaner in some ways, maybe less scaling potential if the brine doesn't boil, and it lets us use much cooler resources.
Yeah.
But the thermodynamics, according to DiPippo, reveal a pretty major operational drawback: waste heat.
A huge amount of waste heat, yes. Binary plants can be quite effective or thermally efficient in terms of how much heat they successfully extract from the brine, but because they're operating with a relatively small temperature difference between the hot geothermal source and the cold sink, usually ambient air or cooling water, they are inherently limited by the basic physics of the Carnot efficiency cycle.
Meaning a lot of the heat just can't be converted to useful work.
A lot of it. The result is that binary plants discharge enormous amounts of waste heat to the environment. DiPippo gives a striking comparison. A typical geothermal binary plant might discharge around 7.7 units of waste heat for every single unit of useful electricity it generates.
Wow, 7.7 to 1. How does that compare to, say, a coal or nuclear plant?
Much higher. A modern, efficient coal or nuclear plant might discharge only about 1.7 to 1.9 units of waste heat per unit of electricity generated. So the geothermal binary plant needs significantly larger cooling systems, massive cooling towers or air-cooled condensers, just to get rid of all that low-grade heat that couldn't be turned into power.
That must add significantly to the plant's footprint and cost.
Absolutely. And within the design of that critical heat exchanger in a binary plant, engineers focus intensely on something called the pinch point.
The pinch point, what's that?
The pinch point temperature difference refers to the smallest temperature gap that occurs anywhere inside the heat exchanger between the hot fluid that's cooling down, the brine, and the cold fluid that's heating up and boiling, the working fluid. You can plot their temperature curves as they flow through the exchanger.
And there's one point where those curves get closest together.
Exactly. That closest approach is the pinch point. Designers want to make this temperature difference, this gap, as small as possible, because a smaller gap generally means more effective heat transfer. You get the working fluid hotter. However, there's a limit. This pinch often occurs right where the working fluid starts to boil. If you try to make that gap too small, the amount of surface area needed in the heat exchanger to actually transfer the required heat becomes impractically large, potentially infinitely large. The cost skyrockets.
So it's a trade-off. You want a small pinch point for efficiency, but not too small, or the heat exchanger becomes enormous and unaffordable.
Precisely. It's a key optimization challenge. And it drives engineers to explore more advanced binary cycle configurations to try and improve efficiency while managing costs. Things like dual pressure cycles, where you boil the working fluid at 2 different pressure levels, or dual fluid cycles, sometimes using a recuperator to capture waste heat from the turbine exhaust to help preheat the working fluid.
Always looking for ways to squeeze out more efficiency.
Always. There's also research into supercritical cycles where the working fluid is heated above its critical pressure, so it never actually undergoes a distinct boiling phase change. It just becomes a very dense, hot fluid. These can be more efficient, but they operate at extremely high pressures, which means you need much thicker, more expensive tubing for the heat exchangers. Again, it's always that cost versus benefit trade-off.
Okay, let's pivot now to look at how these different systems perform in the real world over time. How operators have had to grapple with resource management, dealing with scaling, corrosion, the whole life cycle of a geothermal field. We absolutely have to start with Larderello, Italy, the birthplace of geothermal electricity, and its long, hard battle with corrosion.
Larderello is a classic story. The natural steam that first came out of the ground there was incredibly corrosive. It wasn't pure H2O. It contained significant amounts of non-condensable gases, particularly acidic ones like carbon dioxide, hydrogen sulfide, and things that form sulfuric acid when mixed with moisture.
Nasty stuff. So you couldn't just run that steam through an early 20th century metal turbine.
Absolutely not. It would have just eaten the turbine blades away in no time. So when Prince Piero Gennaro Conti first started generating commercial power there around 1916, he had to devise a really clever but complex workaround, the indirect cycle, sometimes called Cycle 2 in Larderello's history.
Indirect, meaning the corrosive natural steam never actually touched the prime mover, the turbine.
Exactly. Conti used these huge heat exchangers called Kessner evaporators. These were often made of special materials like aluminum or other alloys that could at least partially withstand the chemical attack from the raw geothermal steam. This primary corrosive steam flowed through the evaporators and was used to boil clean, pure water in a separate loop.
Creating a secondary supply of clean steam.
Right, and it was that secondary non-corrosive steam that was then safely fed into the turbine to generate electricity. It was highly inefficient, you lost a lot of energy in the heat exchange, and it was very expensive to build and maintain those massive evaporators. But for decades, it was the only way they could actually generate power from Larderello's aggressive steam.
And they stuck with that complex indirect system for a long time.
For decades, yes. It wasn't really until after World War II when significant advances were made in metallurgy developing new steel alloys that were much more resistant to corrosion and high temperatures that they could finally move away from it. They eventually shifted to what they called direct intake condensing units, or Cycle 3.
Meaning they could finally feed the natural steam directly into the turbines.
Yes. These new materials could withstand the chemical environment much better. This dramatically simplified the power plant design, got rid of those huge, inefficient intermediate heat exchangers, boosted the overall efficiency, and significantly lowered operating costs. A major step forward, enabled entirely by material science.
Okay, next case study, the Geysers in California, world's largest dry steam field, but one that famously faced an existential crisis because its steam supply started running out. A story of resource mismanagement.
You could certainly argue that, especially in the early decades. The Geysers is a perfect, if painful, example of what happens when development outpaces understanding of reservoir sustainability. Over its long history, the field produced just staggering amounts of steam. DiPippo cites over 2 trillion kilograms in about 42 years.
2 trillion kilos of steam removed from underground.
Immense. But historically, the amount of fluid from back into the reservoir through injection was only about 34% of the mass extracted. For decades, far more mass was being taken out than was going back in, or being naturally recharged.
An unsustainable imbalance.
Completely unsustainable. The result was predictable. Reservoir pressure started dropping steadily. The steam output from wells declined sharply. The field's production peaked in the late 1980s and then went into a steep decline. It really looked like the resource might be exhausted.
But it wasn't. What saved it? What was the solution?
The solution required a massive, coordinated, long-term civil engineering effort. Recognizing that the reservoir was essentially running out of water, the operators, working with local government agencies, initiated huge wastewater injection projects. The two main ones are the Lake County Effluent Pipeline, LCEP, and the Santa Rosa Geysers Recharge Project, SRGR.
These are the pipelines bringing treated municipal wastewater into the field.
Exactly. Piping treated wastewater, sometimes over considerable distances and up steep hills, from surrounding communities directly into injection wells strategically placed across the geothermal field. This massive afflux of external water, this augmented recharge, essentially started refilling the reservoir's tank.
So this artificial recharge is absolutely critical now for the geysers' survival.
It's the only reason the Geysers is still one of the largest geothermal producers in the world today. It's stabilized the pressure decline and has even led to increased steam production in some areas. It fundamentally shifted the mindset, too. Steam was no longer seen as a free, infinite resource. It became a valuable, managed commodity.
And that shift probably drove improvements in plant efficiency, too.
Absolutely. When steam was cheap and plentiful, the early plants built by companies like PG&E weren't necessarily designed for maximum efficiency. But later plants, like the SMODGO #1 unit mentioned in the sources, were built after the steam supply became a concern. They were designed with incredible focus on maximizing output from every pound of steam. SMODGEE #1 achieved a gross utilization efficiency of over 70%, which is remarkably high, by optimizing everything: condenser vacuum, turbine blade design, minimizing internal losses. Efficiency became paramount once the resource was properly valued.
A fascinating turnaround. Okay, our final case study takes us to a liquid-dominated field, Miravalles in Costa Rica, and highlights the intense chemical challenges operators can face, specifically with severe mineral scaling.
Miravalles is a great example of the kind of chemical warfare, as DiPippo puts it, that engineers often have to wage deep underground in these liquid-dominated systems. One of their biggest problems was calcite scaling calcium carbonate, KCO3.
Calcite, like limestone or chalk. How does that cause problems in a geothermal well?
Well, the deep geothermal brine at Miravalles is naturally saturated with dissolved calcium carbonate. When that superheated brine flows up the wellbore and reaches a certain depth, the pressure drops enough for it to start flashing into steam. This rapid pressure drop, along with temperature changes and CO2 loss, drastically reduces the solubility of KCO3.
So the calcite suddenly wants to come out of solution.
Immediately, yes. It precipitates out as hard, crystalline scale right onto the inside surfaces of the steel well casing, particularly around that flash horizon depth. This scale buildup could happen incredibly fast, rapidly choking off the flow of steam and water from the well, sometimes blocking it almost completely.
And the only solution was?
For a long time, the only solution was periodic, expensive, and damaging maintenance. They'd have to stop the well, pull out the production equipment, and run a drill rig back in to physically ream out or drill out the hard calcite scale from inside the casing, a very disruptive and costly process.
Not ideal. How did they finally solve it more permanently?
They engineered a really clever solution: continuous downwell calcite scale inhibitor systems. They figured out how to run very thin, high-pressure injection tubing down the outside of the main production casing, or sometimes inside it. Through this tubing, they continuously pump a small amount of a specialized chemical inhibitor deep into the wellbore.
An inhibitor chemical.
Oh.
What does it do?
It doesn't stop the calcite from eventually precipitating, but it interferes with the crystal growth process. It keeps the calcium carbonate dissolved, or at least in a non-staling form, just long enough for the fluid to flow up past the critical flash point and out of the wellbore without depositing hard scale inside the casing. The key is injecting it below the depth where flashing begins. It effectively eliminated the need for frequent mechanical cleaning.
Ingenious. And Miravalles faced another major chemical battle too, didn't they? Acid corrosion, similar to Larderello's problem, but in a liquid system.
That's right. Some of the wells produced geofluid that was quite acidic, which could rapidly corrode the steel well casings and surface pipelines, very damaging. Their solution here was equally specialized. They devised a method to inject a very dilute solution of sodium hydroxide NaOH, a strong base deep inside the production wells.
Injecting a base to neutralize the acid.
Essentially, yes. The sodium hydroxide neutralizes the corrosive acidic components, primarily the H+ ions, raising the pH of the geofluid just enough to make it non-corrosive to the steel equipment by the time it reaches the surface. Again, it's about carefully managing the chemistry deep inside the earth to protect the expensive surface infrastructure and keep the power flowing reliably. Miravalles really showcases that intense, ongoing chemical challenge in many liquid-dominated fields.
So we've really covered a lot of ground today, or maybe I should say a lot of underground. We started with the immense deep heat engine driven by plate tectonics.
Right, contrasting those early ideas of continental drift with the modern understanding from seismic data and seafloor spreading.
Then we moved into that sophisticated geochemical exploration using tools like the silica geothermometer to try and gauge the reservoir temperature from afar, dealing with that tricky steam loss dilemma. High stakes there.
Definitely. And then we detailed the diverse engineering solutions needed once you get to the surface. You've got the rare, relatively simple, dry steam plants.
The Workhorse single and double flash plants optimized using that rule of thumb about the average temperature.
And finally, the binary cycle plants, essential for using lower temperature resources, but having to manage those enormous waste heat rejection loads and the complexities of the pinch point in heat exchangers.
And the case studies, particularly the geysers, really drive home the point about sustainability, don't they?
Yeah.
Geothermal isn't automatically limitless. True sustainability demands really prudent resource management. You have to balance what you take out with what goes back in, whether that's natural recharge or augmented recharge like wastewater injection.
Absolutely. It follows a clear life cycle. Development, sustaining operations, potential decline if mismanaged, and only becoming truly renewable through that kind of smart, long-term engineering and resource stewardship. Extraction has to match recharge.
Which brings us back, I think, to the very beginning and maybe leaves us with a final provocative thought for you. We heard how the very first successful geothermal plants like Larderello needed incredibly complex and expensive indirect cycles for decades just to survive the nasty chemistry of the natural steam.
They had to engineer around the corrosion.
So the question is, what unexpected, perhaps even nastier chemical or deep geological challenge are engineers grappling with right now, deep underground in those experimental high-temperature HDR or EGS projects, as they try to fracture rock and circulate water at maybe 400 or 500 degrees Celsius miles down? What currently unknown chemical demon, what extreme condition might they be discovering that could define the next century of geothermal power?
That's a great question. The subsurface always seems to have new surprises waiting. But as we've seen, the engineers, the geochemists, the geologists, they're getting better and better at anticipating and overcoming them.
The deep earth certainly doesn't give up its secrets easily, but it seems like we're getting closer every year to unlocking even more of its power.